Professor KSK, Iyengar, those days, not much material was available on the classical Indian mathematics or astronomy. Much of work was done later on only by Professor Datta and Singh and many others, from Lucknow University and other places. So not much was known except a couple of books on astronomy which were translated by European Indologists. So anyway, my purpose today is, kindly excuse me if you can't see the written matter there because of the technical problems. It doesn't matter, not much is lost. So I shall try to place before you some glimpses of the development of astronomy and mathematics, mainly astronomy, in India, almost right from the Vedic times up to the Kerala period, ending with the 18th or 19th century when the British education system was introduced here. So coming to the Vedic literature, astronomy in Sanskrit text, of course you can't see it because of, I hope the organizers will improve these things in the days to come. Maybe because not many science lectures are arranged here, that could be a reason why not much of technical improvements have been here. I have been a regular visitor to this center right from my student days at the National College. Then also the similar problems were there. Anyway, I don't go through all those details. The very first shloka is from Vedanga Jyotisha. Vedanga Jyotisha is the earliest Indian astronomical text in Sanskrit. There Jyotisha meant only astronomy and calendrical astronomy and not astrology. Astrology was not accommodated during that period. And the period assigned to this Vedanga Jyotisha is around 1200 BC. And the shloka I have quoted there tells you the importance given to mathematics and astronomy in our traditional Indian system of education or Indian knowledge system. It says, for those who are lovers of Sanskrit, I would be glad to quote, Yatashika Mayuranam Naganam Manayo Yata Tadvat Vedanga Shastranam Jyotisham Murdhanistitam. Another version of the Vedanga Jyotisha tells us Ganitam Murdhanistitam. It doesn't matter. Those days mathematics and astronomy went hand in hand, and astronomy was strangely treated as a handmaid of mathematics. So that was the development we had, and that is the importance given to both mathematics and astronomy. And the next shloka which I have quoted from Vedanga Jyotisha tells us that Vedas were developed for the purpose of performing yagas and yajnas, the sacrifices. And sacrifices or yajnas cannot be performed anytime somebody wants. They are time stipulated, and different yajnas are to be performed on special occasions, time-bound, calendrical system therefore developed in this country. And the shloka says that this is Kalavidana Shastram. Astronomy is called Kalavidana Shastram, the science of time. That is the importance given to astronomy in this country. And side by side, mathematics was also developed because that was necessary. Geometry was necessary for constructions, and algebra and arithmetic were necessary for measurement, counting, and other calculations and things like that. And I don't go into details. Indian mathematics is held in high esteem in the history of world mathematics, and I'm not going to elaborate on that because that's a different subject. And the numeral system followed world over today, comprising 10 symbols, 0 to 9 and 10 based, is India's contribution. And world over it is accepted and it is being used. So those of you who are interested can go through the books. There is a beautiful book called The Universal History of Numbers. The Universal History of Numbers. It is authored by a French scholar, and now the English version is available. And 3 volumes, it has 3 volumes. Of them, the second volume is totally dedicated to India's contribution. And it is the bulkiest volume. And we are proud to go through that, written by a French scholar. And there he quotes and quotes immensely from Western scientists, especially mathematicians and physicists, eulogizing India's contribution to mathematics. Not only European, even Arabic scholars those days, they learned mathematics from India, they learned astronomy from India. It was Brahmagupta's 2 Sanskrit texts Brahmasputa Siddhanta and Khandakadyaka, which were translated to Arabic, and thus the Arab scholars learned astronomy from India, and they practiced Indian astronomy for long, and even today we are told they do compute eclipses according to the Indian procedure. But later they got introduced to Ptolemy's Almagest and started following Ptolemy's procedures. But still, comparatively, they find the Indian procedure far more accurate, far more systematic and things like that. It's not my statement. These are vouched by Arabic scholars themselves. And India, the book by Al-Biruni, is all praise for Brahmagupta. That's something really great. Okay, so those are some of the glimpses here and there. I will begin. The next. A typical Western critical remark on our medieval and ancient Indian astronomers is that Indian astronomers were at best mathematical manipulators and were never good observers. That is a very caustic remark by some Western, mainly British Indologists. But French Indologists, on the other hand, don't agree with these British Indologists. And the French Indologists themselves, they were very good mathematicians and astronomers. They are all praised for what India has done, and particularly Aryabhatta is held in highest esteem. And here, for example, contrary to that criticism that Indian astronomers were never good observers, here the famous Kerala astronomer Nilakanta Somayaji makes a remark about his grand teacher, Paramaguru, Parameshwaracharya. Kerala had the great, many great contributors from after Bhaskaracharya II. Bhaskara II was in the 12th century. He belonged either to Karnataka or Maharashtra, or in the border between Karnataka and Maharashtra. But after that, in the northern region, there was virtually a decay in the development of sciences and also perhaps culture due to so many successive foreign invasions. But in the south, particularly Kerala, became the center of remarkable development in the fields of mathematics and astronomy from 14th century up to about 19th century, and really truly remarkable. It far exceeds in its importance the earlier contributions by Indian astronomers and mathematicians. By and by, I may have mentioned some of them. So Parameshwaracharya, first to come was Madhava in the 14th century. He was succeeded by Parameshwara. His son was Damodara, son and disciple. And his son, his disciple or student was Nilakanta Somayaji, one of the greatest Kerala astronomers. And Nilakanta praises his grand teacher, Paramaguru, Parameshwaracharya, by saying, my Paramaguru, Parameshwaracharya, spent 55 long years astutely observing the planetary phenomena, and based on them, he composed this text called Samadrugganitam. It's called a Karana text, which means a handbook, not a big treatise. But based on his astute observations over a long period of 55 years, he says, Panchapanchashat Varshakalam Niriksha Grahana Grahayogadishu Pariksha Samadrugganitam Karanam Chakara. So 55, now he observed Niriksha, observing, and then Pariksha, critically examining his observations. He composed this text called Samadrugganitam. That's very popular even today in Kerala and elsewhere. So that is, if they were not good observers, how on earth could they have given the parameters and procedures, formulae and all that? They were theoreticians, yes, but certainly based on observations. Before telescope came. Telescope came somewhere in the 15th, 16th century period when Galileo was there. But prior to Galileo, even in Europe, they had only crude instruments for observation. So did India have. And the crude instruments here used in India were not of inferior caliber at all. In fact, Brahmagupta, in his Brahmasputa Siddhanta, has devoted an entire chapter called Yantradhyaya, where he goes on listing the various instruments used for astronomical observations. And when did Brahmagupta live? In the 7th century AD, much earlier than many European astronomers. Incidentally, I may point out that so far as Europe is concerned, after Ptolemy, who was in the 2nd century AD, up to the period of Galileo. So for nearly 14 centuries, there was virtually no development in physical sciences in Europe. During that very period, here in India, we had very remarkable astronomers and mathematicians like Aryabhatta, then Bhaskara I in the 7th century, Brahmagupta is contemporary, then many of them up to Bhaskara the 2nd, and soon after the era of Kerala mathematics and astronomy started functioning, and they have done wonderful things during those 4 or 5 centuries from 14th to 19th century. Next one. I'm not going through all these details, but just to give a glimpse of what the Vedic literature contains by the way of astronomical either phenomena or concepts and things like that. For example, in Vedic literature, in Rigveda, Taittiriya Samhita, then Taittiriya Brahmana, Shatapatha Brahmana and all these texts, you have these astronomical concepts explicitly mentioned. For example, seasons, then nakshatras, day, concept of a day, then equinoxes, 1 or 2 planets in the Vedas. So like that I am not elaborating on them. But so far as nakshatras, in fact Indian astronomy is famous for its contribution to the concept of nakshatras. That is, the zodiacal belt is divided into 27 nakshatras. Why 27? That is because that is the integer value of the sidereal period of the moon. So moon, and it is to observe any heavenly body, whether moon or other planets, their observations are made generally through their closeness to a particular star, bright star, which is visible. Even in China, similar development was there. They too have 27 asterisms. Of course, they don't give the same names as India has given, like Ashwini, Bharani, etc. So, but in Rigveda, you don't have a list of all the 27 nakshatras. Only I think 5 or 6 nakshatras are mentioned because there was no need for them to mention that. That was not meant to be an astronomy textbook. And Rigveda, for their yajnas and yagas, whichever were considered as appropriate or propitious nakshatras, they are mentioned. And some of them are there. But in the Taittiriya Samhita, in Yajurveda, we have the complete list of 27 nakshatras. Even in the Atharva Veda it is there. But sometimes the list would contain a 28th nakshatra also. That is called Abhijit, somewhere near Shravana nakshatra, I think. So, but later on they gave up that Abhijit nakshatra, and only 27 are being used even today. That is what the nakshatras are concerned. Coming to planets, it's a controversial issue. And so far as genuine, accepted, authentic Vedic literature is concerned, like the Rigveda, Taittiriya Samhita, etc., you will see an explicit mention of only 2 planets, namely Jupiter and Venus. Jupiter was called Brahaspati, and Shukra, Venus. But Shukra is not the name used those days. It is referred to as Vena. And it's a literary coincidence or phonetic coincidence that in the European literature it is referred to as Venus. Here in Sanskrit, Vena. It may be just a coincidence. However, such a reference is there because they were the brightest planets these people could easily locate. And I don't find any mention of other planets, though some people may interpret some mantra as to imply the remaining planets, etc. We are not very sure about it. Then about a weekday, this Monday, Tuesday, etc. The word Dina is used there. Sorry. Vasara, the word Vasara, and those of you who do Sandhya Vandanam, you say Soumya Vasare, Brahaspati Vasare, etc. The word Vasara, which means today, Vara, Somavara, Mangalavara, like that, that word Vasara is used only, it appears twice in the Rigveda. But it is not used in the sense of a weekday. It is used in the sense of a day, ordinary dina anta yavadu ಹೇಳ್ತೀವೋ ಅದಕ್ಕೆ ವಾಸರ ಅನ್ನೋ ಪದ ಬಳಸಿದ್ದಾರೆ. And the context in which they use that word, Vasara, does not imply knowledge of the 7-day week. So we understand the concept of 7-day week came to India much later, possibly in the 1st or 2nd century AD. Prior to that, even in the Mahabharata, I said even in the Mahabharata because lot of things are contained in Mahabharata. ನಿಜವಾಗ್ಲೂ ಮಹಾ ಆಗಿರೋ ಭಾರತವೆಲ್ಲೋ ಅದನ್ನ ಯಾರಿಗೋ ಎಲ್ಲ ಮುಂದಕ್ಕೆ ಎಡಿಟ್ ಮಾಡಿಕೊಂಡು many incorporations have been there. That's not my opinion. It is the opinion of highly traditionally knowledgeable scholars at the Bhattacharya Institute and elsewhere who have edited brought out the critical edition of the Mahabharata. So even there, with all accretions, with all later incorporations, no mention of Vigde is there, and certainly not in Vedas or the Upanishads. So it is only a later arrival or importing of the concept of the 7-day week. There is nothing wrong. We can certainly borrow from others as much as they borrow from us. So this is something about like equinoxes. They do mention about equinoxes, the autumnal equinox and the vernal equinox, which we call Vishuva. So the two Vishuvas they mention. I am not going into details. Vishuvas are the days when the day and night are equal. So those days they do mention. And they were performing a particular yajna for 21 days, Ekavimshati, that yajna on the day of the equinox, and then some days before that, and 3 days later, 16 plus 1 plus 3, 20 days, no, I made a mistake, 17 plus 1, 18 plus 21 days. So 3 days after the equinoctial day, and 17 days before the equinoctial day, totally for 21 days they were doing it. The reference is there in the Vedic literature. So many things are like that. I am not elaborating on these, but for those who are particularly interested, I can give references later. So the next one, references to Jupiter. Explicit reference to Jupiter is there, and it is of astronomical importance to us. For example, there is a mantra which says Brihaspati Dishyam Nakshatram Abhisambhavuva in the Taittiriya Brahmana, which means Jupiter in the course of its motion stood exactly in front of the Tishya Nakshatra, which we call conjunction of the Tishya Nakshatra with Jupiter. What is the Tishya Nakshatra? That is the Vedic name for what we today call Pushya. Pushya in modern astronomy is identified as Delta Cancri. So it's a conjunction of Jupiter and Delta Cancri. Possibly it was an occultation, just like eclipse is there. Here also, it is possible that Jupiter was eclipsing the star Delta Cancri, and it is up to our computational astronomers to, in fact, somebody has worked out, there is a paper on that, and it is estimated, and it's not a very frequent occurrence, it rarely occurs, and the scholar who has worked on that has estimated that such a phenomenon of Jupiter going exactly in front of Tishya must have occurred around 4000 BC. There are other astronomical references in the Rig Veda which also almost point to the same period, around 4000 BC. Thereby, we don't hazard a conclusion that Rig Veda was composed in 4000 BC. It's not necessary, but the phenomenon would have taken place that the rest of Rig Veda might have been composed much earlier, but this phenomenon was introduced during that period perhaps. Like that, dating of some of these ancient texts is being taken up by eminent traditional scholars, and it's something worth studying. Like that, many references are there. Then now we come to the mathematical astronomy development in India, which is called the Siddhantic period. Whatever earlier was there by the way of astronomy is called the pre-Siddhantic, that is before Aryabhata. And Aryabhata onwards, we have the systematic development of mathematical astronomy in India, just as Euclid is held in high esteem for developing systematic logical geometry, deductive geometry. Here in India, Aryabhata is highly respected for establishing firm foundation for the systematic development of both mathematics and astronomy. His Aryabhatiyam is a very immensely respected text world over. In fact, the rest of the world respects that text more than we Indians. In fact, if I go on talking that, my criticism will be stronger. So anyway, we know that in Paris or New York or elsewhere, they respect our Indian text very much, and they are experts. They are professional scholars in this field. Aryabhatiyam is a short text having about 121 or so shlokas, and briefly he enunciates all the laws of both pure mathematics and astronomy. And I am glad to have translated that to Kannada with much effort. And if anybody is interested, you can have a look at the text that's available there. In English, it was translated by Professor K.S. Shukla of Lucknow University. He has done a very good job. And it was published by INSA, Indian National Science Academy. I said if I start speaking on that, I will be too critical. And INSA published in 1976, which was the 1500th birth year of Aryabhatta. And after that, now in 2016, ಅದು ಮಾಡಿದ್ದು 1976 ಅಲ್ಲಿ. ಈಗ ಈ ವರ್ಷ they have brought out a reprint. What the hell were they doing for 40 years? Our people don't know how to respect our own heritage. Whereas Germans or French will be very glad to publish such books. And they have been doing it. In fact, they are translating into their respective languages. So here from Aryabhatta, we have a series of great mathematicians and astronomers like Brahmagupta, then Bhaskara II, Bhaskara I, who was a contemporary of Brahmagupta, then Ganesha Devadnya, a Maharashtrian astronomer, and many of them, and Orissa astronomer Samanta, Chandrasekhara Samanta, and then the Kerala astronomers and mathematicians like Madhava, Parameshwara, Nilakant Somyaki, Chitrabhanu, and many of them, till about 18th or 19th century. I am not elaborating on that because some more interesting things would be there, which I try to present before you. So the next one. Civil days in a Mahayuga. See, some basic definitions have to be given in any astronomical text, and so far as the Indian texts are concerned, one of the most important things they have to mention is the duration of a solar year, because for calendrical purposes, solar and lunar calendars have been used in India. Most of our festivals, especially here in Karnataka, Andhra, Maharashtra, these regions, and also many states in the north, they are lunar calendar based, or Ganesha Chaturthi, Sri Ramanavami, Krishnashtami, like that. But in Tamil Nadu and Kerala, as also in one or two or more states in the north, like West Bengal, then 2 or 3 of them, they are using they are adopting the solar calendar, and for them the Sankranti is important, and many other things, even Sri Ramanujacharya's Tirunakshatra. It is based on solar calendar, solar month, but the nakshatra is Tirunakshatra, whatever it is. So that day they celebrate. Whereas in our region, mostly we go by lunar calendar. Both calendrical systems are adopted in India based on the rates of motion of the sun and the moon as seen from the earth. Okay, here are quoted from different texts. The way they give the length of a solar year is not as we today do. We give it as 365.25, etc. But those days, the decimal notation was not there in India. It is the French or the metric system. Our people had to use fractions. To avoid unwanted fraction, what they would do is, they would use a long period, like Mahayuga or Kalpa. Kalpa means 432 into 10 to the power of 7 years. Or a Mahayuga, which is 1,000th of that. That is 4,000 into 10 to the power of 4. In those years, how many revolutions each heavenly body executes? That is the style of their giving, because there is an advantage in giving like that. You deal with only integers, because your denominator is very large. In numerator, I can manage with only integers. I can ignore fraction if given it is there. Error is minimum. So, thereby, for example, in the case of the sun, how many civil days, ordinary days of 24 hours, how many days are there in a Kalpa or a Mahayuga? Mahayuga they have given according to Aryabhatta, Surya Siddhanta and other text. And thereby, you can define the length of a year. Number of days is given. Number of sun's revolutions. Each revolution by definition is a year. So if you divide by the number of revolutions, you will get how many days per year. That is solar year. That's how it is defined. And it works well. It is more or less the same as what we today have as the length of a sidereal solar year. I am not going into details. Generally in workshop, we conduct workshops on Indian astronomy for 2 or 3 days. Then to students, we go on elaborating on these things and we make them work using calculator. So like that each text has given, then revolution of bodies, and what is the rate of motion of each body. For example, if you take the sun, the mean daily rate of motion of the sun as seen from the earth is about 0 degree, 59 minutes, I think it's 10 seconds or something. So slightly less than a degree. Adhe riti ನೀವು moon ತಗೊಂಡ್ರೆ 13 degrees, 10 minutes, something like that. So that is the modern way of writing. Of course, ancients also wrote like that. But there again, the way they have defined is in terms of revolutions in the course of a Mahayuga, as mentioned here. I have quoted different texts, and you will see some variation in the last 2 or 3 digits. That is because these texts were composed during different periods. So over different period, there was great progress in their observations, and based on observations, they went on improving their parameters. That's how you see up to the period, I think, of Bhaskara II, and compared these values with modern suggested parameters also. So that gives an idea to a modern student how good or bad the contents of our texts were. And comparison is very good, and we say, please note that all these were done not by using any sophisticated instrument. They didn't have telescope, by only crude instruments, but a very brilliant mathematical mind. So partly the Western critics are not wrong when they say Indians were very good mathematical manipulators. Manipulators are arbitrary madilla, based on observations, common sense, and many other things. Okay, the next one. Mean daily motion of planets. Using the revolutions I just now mentioned, you can calculate, because number of civil days is given. So revolutions into 360 degrees will give you degrees, divided by civil days. So per day, you will get the mean daily motion. So the mean daily motion of each heavenly body is listed here according to different texts and compared with modern rate also. You will see how almost identically the values tally, even for a fast moving body like the moon. Of course, for a slow moving body like Saturn or Jupiter, there will not be much error. But error generally happens to a fast moving body, and the moon is the fastest moving one. Then the next one, retrograde motion. Many of you will be knowing that when you observe in the sky the motion of the planet, the usual direction of motion of the planet is towards east. Now I am not speaking of rising, setting and all that, but independent of that, the usual rate of direction of motion is towards the east. But if for each planet proper, like Jupiter, Mercury, etc., for a few days, the body appears to move backwards. Actually, it does not move backwards, such a thing does not happen. But due to relative motion, change of velocities of the earth and the body during certain periods, it happens that some of them, for a few days, appear to move backwards. That's called retrograde motion. And in Indian astronomy, it is called Vakragati. Those of you who are in the habit of seeing your horoscopes, or there may be astrologers here, you will see that some planets are shown as Va. In Kannada, they use the initial Va dot, Shani, like that. It means Vakra Shani. Of course, astrologers may interpret it in different ways, but we astronomers recognize it as, due to relative motion, it is the apparent backward motion. It doesn't mean much more than that, so far as astronomy is concerned. Okay, then the values are given. They have given the critical. There are many students of mathematics here. So critical point, you know that when a body moves in a direct direction like this and changes to the opposite direction, there is a critical point. In the calculus language, it will be derivative being 0. And similarly, after moving backward for some time, it changes the course to direct motion. That is another critical point. And it is really, heartening that in our older texts, starting with Aryabhata, they have given the actual critical points when the body changes its direction from direct to retrograde and retrograde to direction. And today, if you use calculus and work out, you will get the very same critical points. The critical point of the angular distance of the body from the sun, it depends on that. When you, for example, if you take Mars, the critical point for its retrograde motion is 164 degrees. That means when the angular distance of Mars from the sun as seen from the earth is about 164 degrees, retrogression starts. And the other critical point is 360 degrees minus 164. I think it is 196 degrees. 196 degrees when that angular distance is there, direct motion will be starting. That's how it is calculated. But what is really surprising is, and please note that these precise values are not given by Ptolemy and his successors. In fact, his successors are least known. And Ptolemy was perhaps the last European astronomer of the ancient times. Up to Copernicus, in the 15th century, we don't have any familiar names in Western astronomy at all. Ptolemy was a great astronomer. His Almagest is really a remarkable text, and I and my research students, we have been studying Almagest as also Copernicus, de-revolution. There are wonderful texts, but the real achievement in our opinion is the Indian contribution. Of course, Copernicus' breakthrough discovery is something to be highly respected, because world over it was believed that the planetary model was geocentric. I mean, there is nothing seriously wrong with it, because we are observing from the Earth. But it was Copernicus who got the credit of proposing the heliocentric model. And incidentally, before I forget, I mentioned this here. Before Copernicus, heliocentric model Copernicus ಕೊಟ್ಟಿದ್ದು. But ಅವನಕ್ಕಿಂತ ಸೀನಿಯರ್ ಅಥವಾ ಹಿಂದಿದ್ದಂತ ನಮ್ಮ ಇಂಡಿಯನ್ ಕೇರಳ astronomer ನೀಲಕಂಠ ಸೋಮಯಾಜಿ, in his famous text called Tantra Sangraha in Sanskrit, he explicitly mentions that all the planets go around the sun. He mentions this. And the sun himself appears to go around the earth. Mathematically, there is nothing wrong in saying that the sun appears to go around the earth due to relative motion. But what is really great is, he mentions that planets go around the sun and not around the earth as was generally believed. And he wonders, why did not our ancients realize this? And he gives credit not to himself, he gives credit to his Paramaguru, Parameshwaracharya. He says, my Paramaguru Parameshwara used to tell me this, that planets really move around the sun and the sun goes around the earth in the course of a year. That's something remarkable. That is prior to what Copernicus gave. And there is a statement by Western critics that Copernicus himself got this idea from Arabic astronomers. In the medieval period, Arabic astronomers were very great, and there is what is called Maraga school in the Arabic region, where wonderful work was done in the field of astronomy. Ulbeck, he was a great astronomer there, and his work is highly respected. Okay, I am not going into those aspects. So this is about retrograde. Then cause of eclipses given by Varamira. And though the common man's belief regarding eclipses would have been that Rahu swallowed full moon or new moon, etc., that is at the layman's level, but the educated class, they were aware of how an eclipse is caused, whether solar or lunar. And Varamira in his Brihad Samhita and Aryabhatta in his Aryabhatiyam explicitly tell us that this is a shadow game. It is due to the shadow that lunar and solar eclipses take place. And there was a belief that you can predict an eclipse based on some omens, shakunagalu. Shakunagalana nodidre grahana agate bidutte gottagutte anta. But this Varamira explicitly criticizes that view. He says that all this is bunkum. There is no shakuna or any such thing which will help you to predict an eclipse. Only by computations and observation you have to predict an eclipse. So they were aware of it, and in their astronomical text they have given the beautiful geometry of the occurrence of an eclipse, and even the mathematical procedures to predict the beginning sparsha, madhya and moksha, the end of an eclipse, and whether it is visible in a certain region or not, whether it is a partial eclipse, annular eclipse or total eclipse. In some Kannada inscriptions, for example, annular eclipse is mentioned. They called it Valaya Grahana, because the usual Sanskrit word is Kankana Grahana. But in Kannada inscriptions, they have used the word Valaya Grahana. So they were observing an annular eclipse. So like that, and here I have explained the geometry of it. And what are Rahu and Ketu? Many of you may be knowing. For eclipses to occur, solar or lunar, either the full moon or the new moon, should be near either Rahu or Ketu. They are just geometrical points. They are the points of intersection of the lunar orbit with the ecliptic. Ecliptic is the apparent path of the sun around the earth. Of course, strictly speaking, the projections of ecliptic and lunar orbit on the celestial sphere are to be taken. However, for the benefit of laymen, often we give the simpler explanation. So those are the imaginary points of intersection of the lunar orbit with the ecliptic, that is sun's orbit around the earth. And they are opposite points, 180 degrees. So in the horoscope, if you see, if you look at Rahu somewhere, exactly opposite to it, Ketu will be there. If in some horoscope it is not like that, you can conclude that the horoscope is written wrongly. Aside, I want to mention a small experiment I did when I was a student in SSLC. ಆವಾಗ ನನಗೆ ಇದರಲ್ಲಿ ಹಾರಸ್ಕೋಪ್ ಬಗ್ಗೆ ಮತ್ತೆಲ್ಲ ಸ್ವಲ್ಪ ಇಂಟ್ರೆಸ್ಟ್ ಇತ್ತು, ಕಲಿತಾ ಇದ್ದೆ. ಇನ್ಫ್ಯಾಕ್ಟ್ B.V. Raman's books only I studied those days. And some classmate of mine was claiming that his father was a very good astrologer. So I wanted to test that. And I knew how to cast a horoscope when I was in SSLC. I cast a pseudo horoscope, a fake horoscope, in which I put all the planets in exalted positions, just as in Sri Ramachandra's horoscope. In Sri Rama's horoscope, 4 or 5 planets are supposed to be exalted. So like that, I cast a pseudo horoscope in which I cleverly put 3 or 4 planets in exalted positions. And I purposely drew Venus and Mercury, the so-called inferior planets, far away from the sun. Those who know astronomy know that Venus and Mercury cannot have an elongation longer than 25 degrees so far as Mercury is concerned, and about 42 or so degrees for Venus is concerned from the sun. That is the maximum. Of course, it slightly changes. But it can't be that 75 degrees or 90 degrees away. But deliberately I put Mercury and Venus nearly 90 degrees, 75 degrees like that from the sun, so that the horoscope would be ideal, better than even Sri Ramachandra's horoscope. And I gave it to my friend, and with all in pretension of innocence, and he believed me. ನಿಮ್ಮ ತಂದೆ ತೋರ್ಸಪ್ಪ, ಆಮೇಲೆ ನಮ್ಮ ಕಸಿನ್ ಹಾರಸ್ಕೋಪ್ ಇದು ಏನು ಅಂತ ಭವಿಷ್ಯ ಹೇಳ್ತಾರೆ ನೋಡೋಣ. Believe it or not, that man wrote a big sheet of paper predicting all the best things in the world. Perhaps even that my cousin, a non-existent cousin, would be an emperor of India. So that way you can test the astrologers whether they know these elementary things, whether Rahu and Ketu are really opposite, and so many things. I'm not going into again so many details. Here is a eclipse days given by Parameshwara. I told you his grand student Nilakanta praised his Paramaguru as a Pancha Shatvarsham and all that. And this Parameshwara, in one of his commentaries, gives a list of the eclipses he actually observed in his Kerala, on the banks of the famous Nila river. He lived there in that region. So whatever eclipses were visible in that region, he has recorded, and they all belong to about 15th century. And in Kerala, they have a unique practice of giving dates, not as is the case in the rest of India. Navella ಏನು ಮಾಡ್ತೀವಿ, ಶಾಲಿವಾನ ಶಕೆ ವರ್ಷೆ and some samvatsara, chaitra mase, shukla pakshe, panchamyam kitau and all that. But Kerala people have a foolproof method of giving the dates. That is by Kali days. Kali beginning, whatever be the beginning, or whatever may be its significance. Take a fictitious date as a starting point. From there on up to today, or any day you want, count the number of days, and there is a method of doing it. So they would give in terms of the Kali days, and that is foolproof. There will not be error even by one day. Whereas if you follow the lunar calendar, as is the usual practice in the rest of India, there is always the possibility of error due to Adhikamasa, Chaimasa and all that. I am not going into details. And when we read inscriptions, you go Bengal nalli yavado ondu date in the eclipse idu inscription and another in Kannada and Karnataka. They refer to the same solar eclipse, they refer to the same actual day, but the mention of lunar month, Tithi, etc. Tithi, of course, it has to be Amartya or Purnima, but the month will be different. ಯಾಕೆಂದ್ರೆ ಅವ್ರಿಗೆ ಅದಕ್ಕೆ ಮಾಸ ಅಂತ ತಗೊಂಡಿರ್ತಾರೆ, ನಮ್ಮವ್ರು ತಗೊಂಡಿರಲ್ಲ. ಈಗ ಏನೇನೋ ಕನ್ಫ್ಯೂಷನ್ ಇರುತ್ತೆ. But when Kali days are given as the Kerala people do, there is not even a day's error. And this Parameshwara gives the list of those eclipses in terms of the Kali days and whether it was solar or lunar and all that. And we have converted that to modern Christian date, Julian or Gregorian, avagella is Julian. Before 1582, it was Julian calendar. Those dates we have computed. And whether it is solar, lunar, weekday and all that. Please note that all the data given by Parameshwara is perfect. And you can verify it by modern computation. So they were really great observers. And much more remarkable thing is, see, one particular solar eclipse, he worked out for his place in Kerala on the banks of the Nila river. And by his computation, he found out that that eclipse, solar eclipse, would not be visible for that latitude of his place. Then he worked out for which latitude nearest that eclipse would be visible. And he found that that works out for the latitude of Gokarna in our Karnataka. And he mentions Gokarna Kshetre Drishtam. So he appears to have visited Gokarna and seen the eclipse and do whatever the rest of it was required. And he mentions that for 2 occasions he mentioned that solar eclipse was not visible in his place, but was visible in Punya Kshetra called Gokarna. So most possibly himself he will have visited, or he might have deputed a student of his. Such very good men of scientific spirit they were. And remember, those days, traveling from one place to another was not easy. There were no roads, no buses, nothing. Even carts were not good. Or even if you go by cart, so many days it would take. They have to cross so many rivers. It's a tough job. And for Orthodox Brahmins, you can understand the problem. They would not even touch water. They would not eat anything. So imagine he's going all the way from Kerala to Karnataka, Gokarna in our North Canara, and observing the eclipse. They were really men of scientific spirit. Otherwise, they would not have recorded all these things. And this is also, I'm not going into it, the procedure of calculating an eclipse, half duration. First, we have to find out exactly at what time the full moon or the new moon takes place. Then, using the latitude of the moon, they knew how to calculate the latitude of the moon. Using that, you have to calculate what is called half duration, So, from the instant of conjunction or opposition, if you subtract the half duration, you will get the beginning of sparsha. If you add, you will get the end of the eclipse or moksha. Astella, they would refine it, they would fine tune, and Brahmagupta gives successive approximations 5 times, 6 times, and today in mathematics, this iterative procedure is a very important thing. Even in modern astronomy, those of you who are familiar with it will be knowing. Even today for computation of solar eclipse, not only solar eclipse, even the time of sunrise or sunset, you have to follow the iterative procedure, not just a single formula. The single formula would give you an approximate time. Other than you fine-tune ಮಾಡಬೇಕು, for which an iterative procedure has to be adopted. And we should congratulate Brahmagupta of the 7th century, who would prescribe successive iterations until the result converges. 6th iteration or 7th iteration, if the amount of error or difference is less than the prescribed error, then it is accepted. In an ordinary mathematical language, they should converge, then only they would accept. This is something remarkable, and Ptolemy has not done that in his Almagest when he speaks of lunar and solar eclipses. So the next one, and total solar eclipse of October 1955. That was considered a very important total solar eclipse, which was visible in India, but not in southern India. Some of you will have watched in the TV, Doordarshan, where you see in the Allahabad, the North Indian belt, the totality of the solar eclipse passed through Allahabad and ended at Diamond Harbour near Calcutta, and that was shown, and our top scientists were there around explaining us the phenomenon and all that. And we have calculated using our Indian procedures, our method and modern values from ephemeris, we have compared, and I am proud to tell you, our Indian procedure almost coincides with what the modern ephemerides give for eclipse computation. This is something remarkable. And Arabic astronomers, even today, I got somebody there in Iran, and a practicing astronomer. He sent me a paper in which he says the eclipse computation even today in that region is done by using Indian method, and it is far easier. The importance of Indian procedure is it's far easier. Using modern procedure, if you want to calculate solar eclipse, it is a very cumbersome process. Only computer can do it. There also this Besselian elements and all that you have to calculate, which is a big headache. By the time the eclipse will have been over. Whereas by Indian procedure, very fast, within half an hour or 45 minutes, you can compute reasonably well. We are not claiming the accuracy is to the extent of half a minute or 10 seconds. But even if there is an error of 1 or 2 minutes, you should not mind it. But the procedure, Indian procedure is extremely simple. So like that, again, those are tables you can show. Special features of Grahalagam. There is a text called Grahalagam on astronomy. It is composed by a Maharashtrian astronomer by name Ganesh Devatya. He is highly respected, so also his text Grahalagam. The reason is, he is the first astronomer, I think, in the world who has totally dispensed with trigonometry. Any serious student of astronomy would ask, how on earth can you have astronomy, spherical astronomy, without spherical trigonometry, sine, cosine and all that. Without that you can't do astronomy. But here is this author of Grahalagam who totally dispensed with sine and cosine. Why did he do that? Because this trigonometry was a big bugbear for the Panchanga makers. These Panchanga makers are not necessarily good in mathematics and not necessarily even good astronomers. But it is a family profession. My grandfather did it, my father did it, I should do it, even if I am a monk. Otherwise, I have no other way of livelihood. So I have to compose Panchanga. So for them, trigonometry was a big bugbear, as I said. And this man, Grahalagam author, simplified. How did he do that? He replaced the trigonometric function sine by a very good algebraic approximation. Then again, for the first time in the world history of mathematics, it is Indian mathematician Bhaskara I of the 7th century who gave a very beautiful approximation for sine, an algebraic approximation, which you can use even for large angles. We were been working in applied mathematics. We know we often use the approximation sin theta approximately theta when theta is small and in radian. While working the problem on pendulum, you will have done it to reduce the differential equation to first order. But please note that sin theta approximately theta in the theta in radian is a very bad approximation. It is valid only for small values of theta. That's why our physics teachers would tell us when we do experiment on simple pendulum, the amplitude should be small. But ನಮಗೆ ಯಾವ physics maestro amplitude ಎಷ್ಟು ಚಿಕ್ಕದಿರಬೇಕು ಅಂತ ಹೇಳೇ ಇಲ್ಲ. For me 45 degrees was good enough. So I used to, so that experiment would be completed in short time. But against 2 degree ಇರಬೇಕಾದ್ರೆ. But if you tabulate the values, it is very bad for say 10 degrees, 15 degrees like that. But I am happy to tell you that Bhaskara's approximation is a very good approximation for sin theta, and theta can be very large also using the allied angle formula, sin of 180 minus theta, 180 plus theta and all that, correct to 3 decimal places. Why not we congratulate that Bhaskara one? Sure. But Bhaskara one himself ಅದನ್ನು ಯೂಸ್ ಮಾಡಲಿಲ್ಲ ಅಷ್ಟೇ ಅವನು ಹೇಳಿದ್ದು. But later Indian astronomers like Sripati Bhatta in the 10th century, Bhaskara II in the 12th century, and completely in the early 16th century, this Grahalagam author, Ganesh Devatya, fully utilized that formula, and the entire procedures of astronomy was simplified by this Ganesh Devatya. And today, the entire North India, Maharashtra, and our North Karnataka, they do use this Grahalagam for their Panchanga competitions annually. These are pictures of annular solar eclipse, total solar diamond ring. It looks like a diamond ring, and it occurred at the place called Diamond Harbour near Calcutta in the 1995 total solar eclipse. And annular eclipse was observed in Trivandrum, Kanyakumari, in that region, I think a couple of years ago, and those were also shown over the TV. I think I should stop here. Okay. If you have any questions to ask, you can. But madam?